What is thermodynamic? Thermodynamics is a branch of physics that studies how heat, work, and energy interact. It explains how energy changes from, for example, how chemical energy in fuel turn into heat and then into motion in an engine. Understanding thermodynamics helps us figure out how engines work and how to make them more efficient. Next slide, importance of the first and second law in engine. There are two key laws of thermodynamics that apply to engines. The first law is about the energy conservation. It says energy can be created or destroyed, only change from one form to another. The second law tells us that no energy process is perfectly efficient. Some energy is always lost as waste heat. Both of these laws are very important in how engines use fuel and produce power. Now, let's move to the first law of thermodynamics. The first law is called the law of energy conservation. It means that in an engine, the energy from burning fuel doesn't disappear. It becomes heat, and that heat pushes the piston, turning into work. For example, in a diesel engine, fuel burns to create heat. The heat increases pressure, and that pressure moves the piston. Next, its second law of thermodynamics. The second law introduces the ideas of entropy, which is basically disorder. It tells us that in every energy conservation, some energy is always lost, usually as heat, so no engine is 100% efficient. In diesel engines, for instance, only around 35 to 45% of the fuel energy become useful work. The rest is lost as heat through the exhaust and engine surface. Now, let's move to comparison of the first law and second law of thermodynamics. So, the first law is about energy conservation. It tells us that energy can be created or destroyed, only change from one form to another. In engine, this means the chemical energy is fuel becomes heat, and then that heat becomes mechanical works to move the piston. The total amount of energy stays the same, it just change form. But the second law adds an important reality. Not all of the energy become useful work. It tells us that during any energy transformation, some energy is always lost, usually as waste heat. This is because of the concept called entropy, which is the measure of energy that is no longer usable. So, in real engine, even if we burning the fuel perfectly, we can never convert 100% of the energy into useful work. Some of it escape as exhaust heat, friction loss, or heating to engine part. To summarize, the first law tracks where energy goes, while the second law explains why engines are never perfectly efficient. Both laws are crucial for designing better engines.
Next, I will talk about what is Diesel cycle. Diesel cycle is the idealized thermodynamic cycle for compression ignition engines. Ideal means that we assume it has perfect conditions, which the perfect conditions are no heat losses, instantaneous combustion, and reversible adiabatic processes. Diesel cycle consists of 4 processes, including adiabatic compression, constant pressure heat addition, adiabatic expansion, and constant volume heat rejection, and it operates on the principle of constant pressure combustion. Lastly, Diesel cycle relies on compression ignition, where fuel is injected at high pressure and ignites spontaneously due to air compressed to high temperature. There are 4 key processes of Diesel cycle. The first one is adiabatic compression, where the piston compresses the air in the cylinder and no heat is exchanged, which means Q is equal to 0. Pressure and temperature increases significantly and work is done on the gas. So if we see from the PV graph later on, the steep will curve upward, and for the TS diagram, the vertical upward line shows that the entropy is at constant. The second one is constant pressure or isobaric heat addition, where fuel is injected and combusts at constant pressure. Temperature and volume increases, and which means that heat is added, so Q will be more than 0, and work is done by the gas during expansion. So in the PV diagram, for constant pressure heat addition, they will show a horizontal line upward to the right, and for TS diagram, the curve will be upward, which means that entropy is increasing. The third cycle is adiabatic expansion, where the gas expands rapidly and cools, and there will be no heat exchange, which means Q is equals to 0, the volume increases but pressure and temperature drops, and work is done by the gas, which is a power stroke. So from the PV diagram, the stick will curve downward, and for the TS diagram, it will show a vertical downward line, which means entropy is constant again. And the last stage in the cycle is constant volume heat rejection, where the heat is rejected at constant volume, so pressure and temperature will drop, and which makes it no work is done. And the PV diagram will show a vertical line downward, and the TS diagram shows a curve downward, where it means that entropy decreases.
Okay, in this part, I will explain how the piston works in this cycle. First, during intake stroke, the piston moves downward as the inlet valve opens, cooling air into the cylinder. Then, in the compression stroke, the inlet valve closes and piston moves outward, compressing the air and raising the temperature. As we enter the combustion or power stroke, diesel fuel is injected just before the piston reaches the stop. The heat causes the fuel to ignite, forcing the piston downward. Finally, during the exhaust stroke, the piston pushes back up and the exhaust gases are expelled through the exhaust valve. This entire cycle repeats rapidly, turning fuel into mechanical works.
Now I'll present about PV diagram. So the PV stands for pressure and volume. The PV diagram of the diesel engine cycle consists of two adiabatic lines representing adiabatic compression and adiabatic expansion, and it also consists of two horizontal lines representing the heat addition and rejection processes. This cycle moves in clockwise direction, exemplifying how the engine state changes through the four stages represented by points 1, 2, 3, and 4 from the image on my right. As you can see from the image, point 1 until 2 shows a curve upwards, which represents adiabatic compression. This is where the pressure and temperature increases significantly because the piston compresses the air in the cylinder. Next point 2 to 3, which represents heat addition. This is where the fuel is injected and combust at constant pressure, and that's why there is a horizontal line which shows the constant pressure. And then point 3 to 4, it is a steep curve downward, which says that the gas expands rapidly and cools rapidly too. This is where volume increases and pressure and temperature drop. That is why the curve is downwards. Lastly, point 4 until 1, which is a horizontal line to the left. This is where heat is rejected at constant volume, and then it shows that the pressure and temperature drops. And lastly, the TS diagram. TS stands for temperature entropy. The TS diagram of diesel engine cycle illustrates how heat and work interactions occur during the cycle's four distinct processes. So the vertical and curved lines represent isentropic, adiabatic, and reversible processes, and also heat transfer processes respectively. So this cycle also progresses clockwise, and the area enclosed by the loop represents the net work output of the cycle. So as you can see from the image on my left, for the TS diagram, point 1 until 2 for adiabatic compression shows a vertical upward line, and that means the entropy is constant. Whereas point 2 until 3 is the stage where heat addition begins. For the TS diagram, it is a curve upward, and it means that the entropy is increasing. Point 3 until 4 is where adiabatic expansion happens, So at the TS diagram, it shows a vertical downward line, and since it's a vertical line and it's going downwards, so entropy is constant during that stage. And lastly, point 4 until 1, where constant volume heat is rejected. So the TS diagram shows the curve going downwards, which means entropy is decreasing.
Now, for my part, I'm going to explain about the thermal efficiency of the cell cycle. First, the cell cycle is comprises of 4 processes, which is process 1 to 2 isentropic compression, 2 to 3 constant pressure heat addition, 3 to 4 isentropic expansion, and 4 to 1 constant volume heat addition. The term that will be used in this formula, which is K equals to specific heat capacity at constant pressure divided by specific heat capacity at constant volume. Next, the cut-off ratio, RC equals to V3 divided by V2. As cut-off ratio is the ratio between the start and the end of the combustion phase. The combustion phase involves process 2 and 3, therefore we use V3 and V2. So the formula for thermal efficiency is net work divided by Qin. Qin is the heat supplies at constant pressure. That's why we will use Cp, the specific heat capacity at constant pressure. And heat supplies is during the process 2 to 3. Therefore, the formula for Qin is equals to Cp times T3 minus T2. Next, Qout. Qout is heat rejected at constant volume. The process of heat rejection is during process 4 to 1, and for constant volume, we use Cv, which is specific heat capacity at constant volume. Now we got the formula for net work, which is Qin minus Qout, and just plug in the formula and we get the final formula for thermal efficiency for the cell cycle. Now we will try using the cut-off ratio and the compression ratio. We will be substituting the value for T2, T3 and T4 in the equation to get the final equation. Using this final formula of thermal efficiency of the cell cycle, if we use the same compression ratio for Otto cycle and the cell cycle, we will obtain the result of thermal efficiency of Otto cycle to be greater than the cell cycle. This is because for Otto cycle, the formula for its thermal efficiency only involves the first part of the cell cycle formula, which is 1 minus 1 divided by RK minus 1. Next, how does thermal efficiency relates to the second law of thermodynamics? One of it is that thermal efficiency will always be less than 100% because not all heat energy will be converted into work, some of it will be rejected during the cycle. Just like what my group members have presented just now, that the second law of thermodynamics is that no process is 100% efficient. For comparison between this cell cycle and Otto cycle, the first one is the engine type used. For this cell cycle, it uses compression ignition engine, where air is compressed at high temperature to ignite the fuel, while for Otto cycle, it uses spark ignition engine, where spark plug is used to ignite the mixture. The second one is that heat addition is at constant pressure for this cell cycle, while heat addition is at constant volume for Otto cycle. These processes occur during process 2 to 3. The third one is about the fuel type. The cell cycle uses diesel because it is less volatile and is more suitable to be injected directly to the combustion chamber, while petrol or gasoline is the most suitable fuel to be used for Otto cycle because they are volatile and readily vaporize, making it easy to be mixed with air. The fourth one is about the compression ratio. The cell cycle have higher compression ratio to be compared with Otto cycle that have lower compression ratio. The range of compression ratio for the cell cycle is about 12 to 24, while for Otto cycle is around 6 to 10. The fourth one is ignition. The injected fuel, it will be ignites upon contact with the hot compressed air, making it an auto ignition for the cell cycle. For the last comparison, it is about the application. For this cell cycle, because it have higher torque and better fuel efficiency, they are more suitable to be used for heavy duty machine such as truck, buses, excavators and bulldozer. They also have the ability to withstand the stress of the continuous heavy duty operation. While for Otto cycle, because they convert gasoline or petrol into motion, they are more suitable to be used for smaller machinery such as cars, motorcycle and lawnmowers. Next, we will be moving on to the comparison between compression ignition and spark ignition. First, we have two diagrams comparing the components between the compression ignition and spark ignition. Then, for compression ignition,
air is compressed to a high temperature, allowing self-ignition, while for spark ignition, spark plug is used to generate ignition. Next, air is added first, compressed and heated, then fuel is injected into the cylinder, while for spark ignition, air and fuel petrol mixture is inserted through a carburetor. For compression ignition, they have higher compression, therefore, stroke length is longer, which leads to lower speed of the piston. Spark ignition, they have lower maintenance because of clean fuel, making less carbon emission and piston rings remain clean. The last one is that for compression ignition, rapid combustion at higher pressure takes place. This makes it more intense that leads to louder pressure fluctuation combustion. Therefore, compression ignition produces more noise compared to spark ignition.
Engines are used. First, diesel engines are used in truck and buses. It's reliable for long-haul transport and heavy payloads. These engines often producing 500 to 5,000 horsepower in turbocharged models, power essentials freight and passenger transport system. Diesel engines provide high torque at low RPM, ideal for climbing and towing. Then, diesel engines are also used in ships and marines, which is it's for large marine engines. Use diesel for durability and also efficiency fuel. Then, lastly, diesel engines are used in industrial machinery. Due to their tremendous torque, diesel engines are frequently employed in heavy-duty construction machinery, including bulldozers, loaders, and excavators. You must be asking, why must diesel? Because diesel has higher thermal efficiency, which is it has higher compression ratios with better fuel conversion. Diesel engines typically operate at compression ratios between 14 to 1 and also 22 to 1. Its higher compression ratios raises the temperature and pressure of the air before fuel injection, allowing for more complete combustion. The efficiency increases with compression ratios in thermodynamic cycles, which per the equation, where R is the compression ratio. This is then diesel is better fuel economy because it's up to 20 to 30% more efficient than gasoline engines. Then diesel also high torque output, which is ideal for towing, load carrying and start-up power. Its generating superior torque is a well-known characteristic of diesel engines, particularly at low speed. This torque translates into remarkable capabilities for towing, hauling and big loads. Diesel engines supply the necessary power for effective operation in everything from trucks to marine vessels. Okay, then its reliability in challenging conditions, which is diesel engines perform well compared to other engines which may struggle. It's reliable even harsh temperatures and high altitudes. Its compression ignition technology reduces the likelihood of ignition problems. Diesel engines have a robust and durable architecture, which is the fuel has a greater flash point and lower volatility, enhancing safety. These qualities make diesel engines ideal for industrial and off-road applications. The emission control technologies. Diesel particulate filter (DPF) are devices used with diesel engines to reduce particle emissions. This will capture and burns off soot, regenerates automatically at high exhaust temperatures. Then, selective catalytic reduction (SCR) is an advanced emissions control technology system that reduces NOx by injecting a liquid reducing agent through a special catalyst into the exhaust system of a diesel engine. Uses the reducing agent urea and glue to convert NOx into nitrogen and water and CO2. Very effective catalyst technology in reducing diesel NOx emission to levels required by modern emission standards. And lastly is exhaust gas recirculation (ECR). It's will recirculate portion of engine exhaust gas to lower combustion temperature, reducing formation of NOx. The emission control technologies. Diesel particulate filter (DPF) are devices used with diesel engines to reduce particle emissions. This will capture and burn off soot, regenerates automatically at high exhaust temperatures. Then, selective catalytic reduction (SCR) is an advanced emissions control technology system that reduces the NOx by injecting a liquid reducing agent through a special catalyst into the exhaust system of a diesel engine. Uses the reducing agent urea and glue to convert NOx into nitrogen and water and CO2. Very effective catalyst technology in reducing diesel NOx emission to levels required by modern emission standards. And lastly is exhaust gas recirculation (ECR). It will recirculate portion of engine exhaust gas to lower combustion temperature, reducing formation of NOx.
To summarize, the diesel cycle involves four main thermodynamics processes. First, the isotropic compression, where the air is compressed. Then, heat is added at constant pressure when the fuel is injected and burned. Next, we have isotropic expansion, where the piston moves down and perform works. Finally, heat is rejected at constant value before the exhaust. As we can see in PV and TS diagram, each stage has clear pattern in pressure and temperature changes. The efficiency of the diesel cycle depends on compression ratio and cut-off ratio. Compared to Otto cycle, the diesel cycle is more efficient and use compression ignition, meaning it does not need a spark plug to ignite the fuel. In conclusion, the diesel cycle is more than just a theory. It is the foundation of many real-world applications we depend on every day. Whether it's powering long-haul trucks, running construction machinery, or generating electricity, diesel engines remain critical thanks to their efficiency and reliability. By understanding how this cycle works, we can contribute to improve engine performance, fuel economy, and reducing harmful emissions. Thank you for listening, and I hope this presentation helped you appreciate the importance of diesel cycle in both engineering and everyday life. Bye.